Hi, I'm Kristen, the lead systems engineer of the Scarlet Spacehawks. The problem we set out to address this year was to create a lunar mining robot prototype for the NASA robotic mining competition team. The primary mission of the robot is to dig 30 to 45 centimeters deep into a simulated lunar regolith and then deposit that regolith into a collections bin on the outskirts of the arena. The team held a concept studies meeting to determine the best excavation system for this year's robot, taking into consideration things such as the weight, the excavation capacity, the size, and various other constraints. We also took into consideration the COVID-19 effects in the school and determined, based on lab availability and materials availability, what would be the best system for us to use. When the design had been finalized, we also performed a stress analysis and ANSYS. We've performed that analysis on things such as the wheels, the chassis, the trench digger, and the hopper, which is also known as the collections bin. From this analysis, we were able to gather that the robot would be able to cope with the stresses in the arena. We determined the primary stakeholder for this competition would be IIT, as they both support and fund the Scarlet Spacehawks competition, as well as NASA and the Artemis missions, and researchers interested in either mining robots or interplanetary robots. As I mentioned previously, the team this year chose to use a trench digger conveyor belt type system. This system would allow the robot to reach the intended depth of the competition with a minimum weight added to the entire robot. The way the robot works is that it's powered by external batteries which are housed in an e-box, and the robot can be controlled either through an Xbox controller or semi-autonomously through a LiDAR system, with LiDARs positioned both in the front and the back of the robot. There are separate motors for each of the wheels, as well as the trench digger conveyor belt system, the hopper, and then there are linear actuators to also control the trench digger. Each of these can be controlled individually or as a whole system. Were the competition to be held this year, the robot would start off at a starting position within the arena and then move, hopefully avoiding obstacles along the way, to a viable position within the arena. From there, it would lower the trench digger, and the first 30 centimeters it would remove the baby powder-like substance until it hits the 30 to 45 centimeter, which is the simulated lunar regolith. As it's digging through, it'll deposit that regolith into the hopper bin. From there, once the hopper bin reaches 1 kilogram or more, the robot will be moved over to the edge of the arena and place that regolith into the collections bin. In the next section, you'll see a short demonstration of our robot in action.
Oh.
Over the past few years, the Scarlet Spacehawks have prioritized community outreach. We've worked with local schools and community family nights, and recently we've held educational lesson plans on coding and Arduino programming and lab tours, all completely virtually. We're constantly adapting our outreach events so people of all ages can attend, and will continue to be a fixture in the local Chicagoland area. On behalf of the Scarlet Spacehawks, we'd like to thank Dr. Mahesh Krishnamurthy, NASA, and IIT for their support during this entire competition. We could not have done it without you.